Look closely at your surroundings, and matter is constantly shifting. Iron breaks down into brittle rust. Food left out spoils and sours. In chemistry, this is a chemical reaction, a specific process where starting substances break apart and rearrange to form entirely new materials. These newly minted substances do not behave like their predecessors. They possess completely different physical structures and chemical properties. To the naked human eye, watching a solid metal dissolve or milk curdle looks like unpredictable random chaos. But zoom in to the atomic level, and that chaos disappears. Every single transformation is bound by an unbreakable, invisible system of strict mathematical accounting. By mapping this architecture of chemical change from raw physical observation to predictive mathematical models, we can decode the rules that govern all matter. To build this mathematical model, we first need to know when a reaction is actually taking place by looking for specific macroscopic clues. Matter signals a chemical shift through observable indicators, a sudden change in state or color, a drop or spike in temperature, or the rapid evolution of a gas. This diagram illustrates a classic physical experiment, the burning of a magnesium ribbon in air. The observable inputs are solid magnesium and oxygen. Apply a heat source and they react to produce a dazzling white flame, leaving behind a fine white powder known as magnesium oxide. To standardize this observation, we write a word equation. Starting ingredients, the reactants, go strictly on the left. Newly formed outputs, the products, go on the right. An arrow is placed between them, pointing toward the products to show directional flow. We streamline this by replacing the words with chemical formulas. Mg plus O2 yields MgO. This is known as a skeletal equation. It correctly identifies the specific chemical players involved. However, as a functional model, it contains a critical error. Count the oxygen atoms. We input 2 atoms of oxygen on the left, but only 1 appears in the product on the right. This skeletal equation suggests an atom vanished into nothing, which directly violates the laws of physics. That physical boundary is the law of conservation of mass. During any chemical reaction, mass can neither be created nor destroyed. The total number of atoms for every element must remain identical across the reaction horizon. An unbalanced equation is a physical impossibility. To fix this, we balance the ledger. Let's use the reaction between iron and steam as our primary case study. Fe plus H2O yields Fe3O4 plus H2. This table breaks down the hit and trial balancing method, counting the exact atoms for each element on both sides. The first absolute rule: draw a box around each formula. You cannot alter the chemical identity inside. You only adjust the multipliers outside. The strategy starts by balancing the compound with the maximum number of atoms. Here, we target the 4 oxygen atoms on the right side. Placing a 4 in front of water balances the oxygen, but multiplies our hydrogen to 8, misaligning it. We sequentially address hydrogen by adding a 4 to the H2 product, then balance the iron by placing a 3 on the reactant side. We verify the ledger. 3 iron atoms, 8 hydrogen atoms, and 4 oxygen atoms exist on both sides. The math is flawless, but incomplete without defining physical environments. As shown here, we add state symbols: S for solid, L for liquid, G for gas, and AQ for aqueous. The G next to H2O explicitly confirms this iron reacted with steam. A perfectly balanced chemical equation is a rigorous, mathematically sound proof of physical reality. With the mathematical ledger secured, we can analyze the structural patterns of how these atoms are actually trading places. The most straightforward structural typology is a combination reaction. This chart shows how 2 or more reactants fuse together. Look at the formation of slaked lime. Solid quicklime combines with liquid water to output a single, distinct product, releasing intense heat in the process. The direct inverse of this behavior is a decomposition reaction, where a single reactant breaks down into simpler products. Tearing apart atomic bonds requires an energy intake. This diagram shows thermal decomposition, where external heat energy forces lead nitrate to break apart. In this specific breakdown, the emission of toxic brown nitrogen dioxide fumes serves as a clear macro indicator that the decomposition is happening. But heat is just one tool. Passing an electrical current through acidified water forces an electrolytic decomposition into hydrogen and oxygen gas. Alternatively, exposing silver chloride to sunlight drives a photolytic decomposition, separating out the silver metal. A completely different structural pattern is the displacement reaction, which relies entirely on hierarchy rather than energy intake. Displacement is dictated by relative reactivity. This experiment diagram shows an iron nail placed in blue copper sulfate. Because iron is a more reactive metal, it forcibly evicts the weaker copper from the compound, taking its place and turning the solution light green. If two compounds mutually exchange ions to create a new insoluble solid, that solid settles out of the solution, creating what is known as a precipitation reaction. By categorizing these typologies, chemists can look at a set of starting ingredients and accurately predict their structural output. When clear liquids collide and a dense solid rapidly forms, it is easy to view chemistry as a purely visual, physical event. We began by identifying these physical indicators, but to understand them, we had to enforce the invisible laws of mass conservation on paper. Balancing the atomic ledger ensures that our theoretical models align precisely with the strict physical truths governing atoms. Once those equations are balanced, classifying them into combinations, decompositions, and displacements provides us with a structural map of matter. We stop being passive observers of seemingly chaotic reactions and instead gain a predictive framework. The balanced chemical equation is the mathematical blueprint of all physical matter.